Julie. I know it's the that's two.
$7:30. Being what the day is doesn't mean people should be late. Well, there was an accident on the 78. It took me 40 minutes to get here. Yeah, that might be it. South is closed still, but I think it is probably here. The good thing is this lecture is, I do it because each time I ask if I should keep it, and overwhelmingly, usually the students want me to keep this lecture. And it is just review of other representations of numbers. So binary, complements, case plus, like that. So there are many different number types. We use decimal typically because we have 10 fingers, right? So having 10 digits, 0 through 9, is very useful for us. And then there is the larger class of just integer numbers in general. So it's just counting numbers, whole numbers, right? Negative and positive, because you have unsigned and signed. And these are mostly used in computer architecture as addresses, because typically you don't have address 1.5. It's going to be 0, 1, 2, 3, right? And for these addresses, typically they're going to be unsigned as well. You don't usually think of something having a negative address. And then for signed numbers, these are going to be used in arithmetic calculations. So your add, subtract, multiply, divide. And these can be positive or negative, but there are also unsigned versions. And then we also have floating point numbers. So these are used for applications where you need better precision than fixed point or integers. And you need to go up to like either really, really large numbers or really, really small numbers. And there are two different standards. They're both from IEEE. They're single precision, which is 32-bit, and double precision, which is 64-bit. We're going to start with the basis, which is binary numbers. Okay. So unsigned binary integers. So each position has a different value. It works the same way that our decimal system works, except it's in powers of 2 rather than powers of 10. And that's because there's only 2 digits, 0 or 1. Whereas decimal, we have 10 digits, right? 0 or 10. So the first position is just 2 to the 0, whereas in decimal, it's 10 to the 0. So it's really just indicating the ones place. But the ones place in a binary only goes up to 0 or 1. As soon as you hit 2, you're going into the next digit. So the second position is just going to be 2 to the 1, 2 to the 2, 2 to the. Whereas in decimal, we have 10, well, 1 because 10 to the 0, and then 10, 100. So from that, we can come up with this equation to convert any binary number into its decimal form. Or you can also see this as I have this decimal number. If I wanted the binary representation, this one would as an equation. So you can see here this array of x's is the binary number. So each one of these being 0 or 1. And if x sub 0 or the to the 0 bit is 0, it's just not included, right? So multiply 2 to the 0 by 0 because I don't have anything in place. Whereas if 2 to the 1 place is 1, then I add 2 to my decimal representation, and I just keep doing that until I get to the end of the number. Right. All good with this? So here's our example. Since we're all good with this, let's do this one together, right? So I'm going to start from the right because why? Why does it make sense to start from the right in this case? It's easier to start with the zeros and just move your way up.
Binary.
What's more specific about this 16-bit number? That makes sense to start from the right. Yeah, it's very small. So all of these are 0, right? So I don't really need to think about that. They're all just going to cancel out the 2 to the power of 15, 14, right? I can just start all the way from the base. So 2 to the power of 0 is
1.
Yep. So I add
1.
1. Yep. 2 to the power of 1 is, so I add, so I have 3, right?
Yeah.
And then I have a 0 here, so 2 to the power of 2 is not going to be added. And then 2 to the power of 3 is 8. So 8 plus 3, 11. So this is 11. Right. Here's the equation, right? Coming from here, all of these zeros, because they're all zeros, they're going to multiply that 2 to the power by 0. And then we have 2 to the 3, 2 to the 1, 2 to the 8 plus 2 plus 1 is 11 in base 10. Okay. So from this, if you are using unsigned binary numbers, your range of representation is all the way from 0 to 2 to the power of n, which is your number of bits, minus 1. So if we have 16 bits, like this number, our maximum number is 55,535. Smallest number is just. And when we talk about the rightmost bits, we're talking about least significant bits. So LSB is least significant bits. What's the leftmost bit? The highest. What's the more formal name for it? Least significant bits. Opposite of least is most significant bit. Okay. So here's some more examples. So anyone wants to tell me what this number is? Well, yeah. That's 8 plus 4, right? 12. This one? So this is what? 16? And then plus 11, which we saw before. So yes, 27. Here? Also 12, right? Again, and kind of skip all of this. That's all zeros. Right, so 7 in decimal. What is it in binary? 0, 1, 1, 1. Is what you said? Yep. 1 plus 2 plus 4. Okay. 23 in decimal.
1 0 1 1 1.
1, 0. So 7 plus 16. Right. So the other thing that I do want to mention is that you can extend the integer representation to be fixed point. So if we wanted to represent fractions, we would need fixed point numbers or floating point numbers. But let's start with fixed points. So all that you're doing in fixed point numbers is defining in the string of digits the decimal points. Then just like in decimal, our 2 to the power, it just becomes negative if it's to the right of the decimal points. Positive if it's on the left. So we have the integer part, and then we have the fractional part. And then our equation is the exact same. It's just now that we have beyond the integer part, we have the decimal point here, and we have the fractional part. So if we wanted 7.75, we can kind of split this up into 2 different problems, right? I need to represent 7, put a decimal point, and then represent 0.75, right? So 7 is easy. We've done this in the previous slide, right? It's
0, 1, 1.
yep, 0, 1, 1, 1. The 0.75 might be a little bit more tricky, right? So yeah, it's let's because you how many of you have seen fixed points? Usually, really not many people have seen fixed points. So it's just an extension though. So 2 to the power of -1. What is this?
1/2.
1/2, right? 0.5. So 0.5 is still not enough, right? So we need 0.5, right? So we'll have a 1 after the decimal point, and then 2 to the power of -2 is
0.25.
0.25, right? Because it's just 1 over 4. So we need 0.25. And then if we add those up, we get 0.75. So it's zeros for the rest. So if we wanted 7.75, it's just 111.11. So those of you that haven't seen fixed point before, does it make sense? Yeah. All right. So this is something that you should have seen. how to get signed numbers in binary representation. So we're going to use 2's complement to represent signed numbers. There are different forms of representing signed numbers. So now we can have a negative number. Okay. And here the first or most significant bit is going to indicate our sign. The most significant bit is sign bits. If it's 1, it's a negative number. It's 0 for non-negative numbers. And then non-negative numbers have the same unsigned and 2's complement representation. So if it's 0, 1, 1, 1, that is still 7. So here's an example. So most significant bit is 1, right? So we know it's negative immediately. And then in order to figure out that it's -4, there are 2 things that we do to this number. What's the first thing?
Reverse every number.
Yeah, so you invert everything. So you get all zeros except for 1, 1, right? And then there's one more thing that you need to do.
You add 1 to the.
You add 1, right? So I add 1, it ripples over to make this 1, and these are still 0. So that is 2 to the power of 2, which is 4. So we know this is -4. All remembering this? Yeah. And then the range for our signed numbers is we can go as low as -2 to the n-1. And the reason that we have n-1 is
The MSB is to determine whether it's positive.
we have this sign bit. And then we can go up to 2 to the n-1. And then we have 2 -1. Because why? Why do we have -1 here, not here?
If you have the 1 and you do the 2's complement, you'll overflow the bit and flip everything.
So it's simpler than this.
If it's all ones, it's the next one minus 1, essentially, like if you have like an 8-bit saying it'd be I guess if the other 7 bits are ones, it'd be the 2 to the 8th minus the 1.
It's also simpler than this.
Because we use 0.
We have 0, right? We basically have 2 representations for 0. All ones, all zeros. Because if you're all ones, you have flip them all. Well, no, not all ones. It's just because 0 is on the positive side. Right. So in order to negate, we take the complement to add 1, right? So invert every single bit. So all ones become 0, all zeros become 1. Add 1 to the result. So here's an example. We have decimal 2, which is 1, 0 in binary. And this is positive because most significant bits. So we want to negate this. First step, invert everything. So all the zeros become 1s. All the 1s, which is just this 1, becomes a 0. Then we're going to add 1. So 1 plus 1, it becomes 0, carry the 1, right? And then 1 plus 0, we just get 1, and then 1, 0, 1, 0, right? So this is just now -2. Right? And if we wanted to convert that, first, add 1, we come back to +2. Right. Example 0. So 0 is just all zeros. -1,
One for the first part.
Yeah. all ones. Right, because you invert, add 1 and it comes. Okay. So -5. This one's a little tricky, right? Basic,
but 0 and 0.
0, 1, 0, 1, 0.
I think. Okay. So 5 is 1,
0.
what?
All ones except at the end is 1 0 1 1.
1 0 1, yes, right? So then invert it all. I get. What do I get? So it was 1 0 1 1. So it becomes 0 1 0 0. Add 1, right? So it is
0 1 0.
as 5 is I have a 1 here and a 1 here. Right? So it's 0 1 0 1. And then I invert it all. So it's this is a 0. This is a 1. This is a 0. And then I just add 1. And then everything else ahead of it was also became 1. So if you're given a negative number in decimal and you need to convert to binary, usually easiest way is not to think straight to the negative. It's going to write it out as positive, then negate it. Okay, and then +8. Positive numbers are easy, right? Just think about them exactly how you did before. So it's 1 0 0 0. And all zeros inside. All right. So question is, what is the largest positive 32-bit number in 2's complement? You can give this to me as just 2 to the power.
2 to 31 minus 1.
Yes. And then the representation is just a 0 up front, all ones. Most negative. Someone else.
1 0 0 0 0 0 0 0.
Yes.
All I got.
What's the in power of 2?
-2. You said
31.
Yeah, negative is completely. And then, like you said, 1 0 0 0. Because when you negate it, this becomes 0. All of this becomes 1. I add 1, right? It ripples all the way to the beginning. And this is what is indicating 2 to the 30, right? Because 0 up to 30. All right. So sign extension. If I want to go from, say, 4 bits to 5 bits, how do I preserve my number while increasing the bit width? So our example here is 8 bits to 16 bits or 32 bits. We want to preserve the numerical value. So this is required for operations with registers that are 32 bits, and some of our instructions use immediates, which are 16 bits. So we need to be able to match the 16 bits with 32 bits. So the way that we preserve the sign is that we just replicate the sign bits to the most significant bits. And then if it is unsigned, we just extend it with zeros, just like you would do in decimal. Right? So if I have this 8-bit 2, and it wants to be a 16-bit 2, I just add all these in. If I have -2, I'm going to take the sign bits and extend it. Just undo. So a good rule is just whether it's signed or unsigned, you want to extend the bit width of it, just take the most significant bit, copy it, however many. And we can just confirm that this is still -2 by inverting everything. Okay. This is a 1. I add 1, becomes 0, 1. 0, 1 is 2. Okay. All right. So beyond binary representation, sometimes it's useful to look at hexadecimal representation because it's more common. So hexadecimal representation is very similar again to binary and decimal, except how many digits do I have now?
16.
So it's base 16. So it gives us this compact representation of very long bit strings. So like your instructions in MIPS are 32 bits, right? 1 word long. Is it easier to look at this 32-bit string, or if I have it in base 16, how many digits am I looking at? Not 2. 32 divided by what? Okay, so 32 divided by 4 is
15.
okay. So I would look at 8 digits rather than 32. Okay. And this is also very popular because computers oftentimes use data sizes that are multiples of 4. Because there's 4 bits per hex digit. Right, so if I have these 4 bits, I can just convert it to the hex version. And hex, we go all the way to from 0 to 9, right? And then we start using the alphabet. So A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Right, so examples. And this is a little chart as a cheat sheet. So we want to convert from hexadecimal to binary. So one thing that could be easy is just convert from the hex to the decimal representation, then take that decimal representation for each individual one. So E is
14.
14. So go to 14, right? And I can just convert 14 because I might not have this chart. So 14 is 2 to the 8th plus, I mean, not 2 to the 8th, but 8 plus 4 plus 2, right? So 12 and then 14. So I would put 1, 1, 1, 0. And then C is 12. So I just did 12 because it's part of 14. So we know it's 1, 1, 0, 0. A is easier to remember. It's 10. I remember it because it's 10, 10. Okay. And then 8 is just going back to the other. You're not using the above 9. So 8 is 1, 0, 0, 0. And then 6, again, same thing. Very simple. 1, 1, 0. This is 4. This is 2. We make 6. And then 4, just put a 4, 2, put a 2, and then 0 is up there. Okay. So I've gone from my 8-digit hex to the 32 bits representation.
So you just memorize it?
No, not memorizing. Right, we're converting it. Because we know that E is 14, and you don't have to memorize this because all you have to remember is that A is 10, so then I can just go B, C, D, E, and then I get 4, so E is 4, right? And then I just convert 14 to binary. And then for the first 4 bits, it's these 4 bits that are representing 14. So you don't have to memorize these things, right? It could be faster. I work with hex a bit, so I know these things, but you don't need to. Okay. You can just convert. Right. So yeah, to convert from binary to hexadecimal, it's going to be a very similar process, right? Except now I'm just going to bundle 4 bits together. What is the hex representation? So this is F, right? This is D. This is H. This is A. This is A. This is 2. And this is 3. This is 1. Right. So we see how this works. Okay. So you're going to be doing this quite a lot for if you're working with the MIPS instructions, converting them, things like that. All right. So here is the first checkpoint. Work on this on your own first. The code for today is 710. And I think the people that are still looking at their phones are just trying to pull up survey still. I don't know, is anyone still thinking about this? So we are well past the threshold. So my answer here is which one? B, right? So the explanation is, what is this? 16. And then what is this whole thing? 9, right? Because 8, 1, so 9, 16 plus 9. 25. Okay. So what is this in text then? What is this? And what is this? So 19. So 0x19 is 15. Alright. So decimal, that represents this. So you have an answer. So we're not at the threshold, and I think it's just read the question again. So talk to each other, discuss what you got. Okay.
It's not the games that we have to do positive or negative. Another part of the ones that has to be about the signs. Yeah. Flipping it. One, and then you add plus one for the two that. That last step where you still have to add the one at the end. That's all. I get too many questions wrong. We can add that last one.
Do they get that one?
Well, previous semester. I had to do a lot of drills for me. I can't do it in my head, so I have to write it down. I get it wrong if I do it in my head. I just start spouting out numbers.
So I think you guys are discussing. I see that a lot of you have changed your answer. Right, so. He is signed now, right? So most significant bit is 1, so we can immediately know that
It's negative.
it's negative. So it can't be A, it can't be B, right? And then to figure out what is the actual representation, this doesn't really mean much to me, right? You can't just say, oh, this is 10, right? So it's -10. That would also be wrong, right? We need to actually convert it. So flip them all. I get 1, 0, 1, and then add 1, I get 1, 1, 0, which is 6. So I know this is -6. Next is. Down to this one on your own. So we're right around the threshold, but I think we don't need to do, oh, now we're past that. We don't need to do pure instruction for this. So what's this one?
32.
32. So usually, oh, the other thing is positive or negative.
Positive.
Right, it's positive. And then this is 32, so we already know that it's larger than 29, larger than 13, right? And then what's this whole thing? 13. So 32 plus 13 is okay, right? Alright, so this one is the last one. We're now unsigned. And we want to fix point binary. Okay, and most of you are done looking around. So again, we are past the threshold. So we're gonna split this problem into two parts, right? I can do the integer part first, which is the left part of the decimal. So I'm looking for 33, so I have the 32, right? Right. And I just need one. So any of them that have this have the correct integer part. So A is a contender and D is a contender and E is still a contender, right? 0.75, I need 0.5 and 0.25, right? That we solved for. So 2 to the -1 and 2 to the -2. So 1, 1. So A checks out, B does not, right? This is 33 points what? 25. Yeah. So A is the correct answer. All right. So, I thought there was only 4, but I guess there's more. We can just do this together. So A is what?
Okay.
Yeah, 10, 10. 2,
So,
this thing, right? So 10, 10, 2. So we just need to check these last two things. So F is all one, right? 1 is 1, so it's D. Okay, there is no reading for next class. I do want to again make sure that this lecture is helpful to you guys. So we're going to vote. I am going to turn around so I don't see. Can you count? Okay. So if you like this lecture to stay, raise your hand.
specific lecture of this class.
I think it's
Okay.
Yeah.
You saw, you peeked. I still have my hand up.
No, this class, this lecture is vital.
Yeah, the whole point is just that I don't influence. You already answered and I was told that it's unanimous there. All right, so I will continue to give this lecture.
Yeah.